fait,
Ouais.
dans ce logiciel-là où tu peux juste demander à ce qu'il te montre le transparent uniquement en cours.
Tu sais où c'est?
Aucune idée. Regarde dans les options, en fait, normalement, tu dois pouvoir l'avoir. Sinon, au pire, ce que tu fais, c'est que tu diminues le côté gauche et puis on peut rester en PowerPoint comme ça.
Parce que je ne vois pas où changer ça.
Bence yavaş yavaş başlayabiliriz isterseniz katılımcılarımızı da bekletmeyelim.
Comment tu fais? Tu veux chercher encore un peu, Laurent,
Bah, ouais, parce que je vois vraiment pas et puis
là, dans les
ça
options
doit
qui
être
sont en bas,
ici.
là, tu sais? Ouais.
Voilà.
Voilà, c'est parfait.
Ok.
Super. Okay, so let's begin. Hello, everyone. I would like to thank you all for joining us for this new edition of Grad Talks organized by the Graduate School of Science and Engineering. So first of all, before beginning, I would like just to introduce Laurent Calvez, who is a friend of mine and also a colleague from Rennes University. So first of all, Laurent has a strong experience in the synthesis of material for about 20 years now. He's got his PhD in material sciences in 2006 at the University of Rennes. Then he spent 1 year as a postdoctorand at the University of Arizona. And he became assistant professor in 2007 and a professor in 2020 at the University of Rennes. His research is mainly focused on the synthesis of functional glasses and glass ceramics transparent in the infrared, and also the study of photo-induced phenomena in the same family of materials. Laurent Calvez is author and co-author of about 180 papers published in international journals, 3 patent book chapters, and over 70 international conferences, about 40 invited lecture or seminars. And he received also several prizes and awards, such as Brittany Young Research Awards in 2011 at the French Academy of Science Lab Award in 2016. And today, Laurent will give his conference on chalcogenide classes and ceramics for infrared applications. So, Laurent, the floor is yours. We're listening to you.
Thank you very much, Rie. Good afternoon, everyone. It's a great pleasure to make this presentation this afternoon, and I really would like to thank all the people who invited me and who gave me this opportunity to present a part of the research work. So today I'm going to talk about chalcogenide glasses and ceramics for infrared application. I just want to show you that in chemistry, there's not only carbon and oxygen, that we can also work without these elements and doing great things. So Uriye just showed you my background, so I'm gonna shift this slide just to show you some things about the awards, but not the main things. I wanted to talk about, after my presentation, the popular science. I mean, we are researchers, but we are also teachers. And even if we can get a lot of awards during our career, for us, it's very important to give the presentation of science as a good good matter for everybody. So what I wanted to show you is that I've also carried out lab visits to middle and high school students. I've done a lot of conferences in middle and high school about the daily life of researcher, about glass also, and also to talk about science in the everyday life. And for people who are not researchers, we've done some exhibitions like a glass object of art and science. And I think it's very important for all of us to spread the science out of the labs. And so this is why I wanted to show you what we have to do out of the labs. So I will now start my talk with a short introductions, and I will talk about the different synthesis and shaping way of glasses. I will show you some infrared glasses application, and then to conclude, I will talk about some very recent work on energy application with all these kind of glasses, glass ceramics and ceramics. So what is a glass? We could give two definitions of a glass. The first one is an operational one. So glass is a solid obtained by solidifying a liquid which did not crystallize. And the other one is glass is a non-crystalline solid. So what is defined as a glass now for the community is that a glass is a non-crystalline solid material that exhibits a glass transition. So I will talk about this kind of material all over my talk now. But what you have to know is that there are a lot of glass families. The main one is well known. It's oxide glasses where you can do window, bottles, etc. But there are a lot of different glasses that are less known, like glasses based on different kind of elements, like fluoride here, chalcogenide glasses. You can see here there are black glasses, so which is not usual because most of the time glasses are used because they are transparent to the visible light. These chalcogenide glasses are based on very heavy element, and even if they are not transparent in the visible, they will be transparent in the infrared, and that's why we will have a look closer to them today. Other family of glasses, metallic glasses based on different kind of metals. These kind of glasses are not common and were discovered pretty recently. It was 20 years ago. And as you can see on this picture, they now can act as bones replacement. And also some glasses that you know because most of us we can use them. It's polymers glasses that we have on our Googles. So today I will talk about only this kind of family of glasses, chalcogenide glasses based on sulfur, selenium, but no oxygen and no carbon. So I will give a brief introduction to infrared. As you can see here on the electromagnetic spectrum of light, there is different wavelength of light, and usually what we know is the visible one, which is from 400 nanometers to 800 nanometers. At lower wavelength, you have UV. At higher wavelength, you have infrared. And today I will talk about infrared. And what is interesting here is that the visible works for us because the sun emits light around 10,000 K, and we can get this kind of light in our eyes and get it. But the infrared light, which is around 100 Kelvin, we can't see it. So we have to develop some technique to observe this light. And this is the context of thermal imaging, which is based on the detection of black body emission. So as I told you, the sunlight emits at 10,000 K. It's very hot, so it emits at X maximum in the UV and also in the visible. But if we take into account some other bodies like human bodies, so if we are not too sick, we are around 300K. So we also emit light, but in the infrared, around 10 micron. And if you want to make the count, we emit approximately 1 watt per kilo. So we emit a lot of light in the infrared. So we need for materials that are transparent in this kind of wavelength. And hopefully we will use also two windows that is transparent to the atmosphere. We can check this curve here. There are three bands of transparency in the atmosphere, the visible one that we will use every day, but there are a second one in the mid wavelength from 3 to 5 micron, and another one in the long wavelength from 7 to 14 micron. And today we'll talk mainly about the application in this kind of wavelength, in the long infrared wavelength. So thermal imaging is still a growing market, even more in the last years because of COVID. We've seen all that in airport and in different hospitals, they used thermal cameras to check the temperatures of everybody. So it's a growing market, but it's still very expensive. So we need for improvement on the miniaturization of detectors, electronics, computing systems. But the main thing is to get cheaper and more efficient materials, because it's this kind of materials that are very expensive. So up to now, the thermal cameras and everything which is working in the infrared used single crystalline germanium, as shown on these pictures. They are very, very expensive, and they need to be shaped by diamond grinding. They are synthesized by Czochralski method. It takes a long time, over several months, to get this kind of germanium single crystals. Or you can also use zinc selenide, some polycrystalline. It's made by a chemical vapor deposition. So it's also a long process, very expensive. And at the end, you have to shape by mechanical grinding this kind of lenses. So there are an alternative here, which are the chalcogenide glasses. This is what we are working on in the lab of REN. Why we want to use this kind of chalcogenide glasses? Because these materials, even if they are not transparent in the visible, they are transparent in the infrared. So very close to the visible, 800 nanometers, up to 16 micron, and even more. They are cheaper because they will use less germanium. And also what is very interesting with glasses, compared to the other materials, is that you can shape them by molding just a very low temperature, just above the glass transition temperature. The main drawback of this material is that you have to make some synthesis in silica tubes. The silica tubes are single-used, so you have to bring them and take back the glass. And also, this kind of glasses present very weak mechanical properties if we compare to window glass. So here are some examples of these chalcogenide glasses, which are black, not transparent in the visible, but fully transparent in the infrared. I will show you here some application of this kind of infrared lenses. Of course, the main one is the military domain. You can see here something in the visible, an image taken in the visible, and here using the thermal cameras. But not only for military application, more and more you can find some cars with assistance for driving. So you have integrated infrared images in the car. It should increase the safety during night and foggy condition. So if we look closer here, we have an image taken in the visible range. So what we can see during the night But if we look closer in the near infrared, you can see here some ice. And if you look to mid-infrared range, even in the night, you can see some people at more than 400, 500 meters. And other very recent application like medical images, quality control. Also, you can help firefighters in foggy and night conditions. So there are more and more applications with infrared, and we are still developing this. So chalcogenide glasses are based on different elements. What are the chalcogenide elements? Sulfur, selenium, and tellurium. But it's very difficult to make glasses with only these elements. So you have to add some other elements, very heavy elements like gallium, germanium, arsenic, and antimony. Like you can see, arsenic and antimony are not so friendly elements, but they are good to make this kind of glass. So these chalcogenide glasses are transparent in the infrared. If we look at this graph, we can see that silica tubes, silica window are transparent in the visible up to 3 micron. And what we will use is sulfur, selenium, and tellurium glasses. And we can see that they are transparent all in the second and third atmospheric windows that we're going to use for all the application. They are very interesting because I told you they present viscoplastic properties, so they can be very easily shaped by molding into lenses or by drawing into fibers. So here you have some example of fibers. How are made these glasses? It's not common. It's not like oxide glasses where it's pretty easy to do, because oxide glasses you can use the melt quenching method in air. But with selenium and with this kind of glasses, you want to avoid oxides because it will absorb the light in the infrared. So you have to do the synthesis in this kind of silica tubes that are placed under vacuum to avoid oxygen and water. So after one night under vacuum, you can seal the tube that you will place in an oven for one night at 900 degrees C. So you will get the liquid inside your tube. And for all the glasses, it's always the same thing. You will have to cool it down very fast. So it's what it's called quenching. So it will go through 900 degrees C to about 300 degrees C in 3 or 4 seconds. And then, because doing this, you will get a lot of mechanical constraints, you will have to anneal the glass to relax the constraints around the glass transition temperature. You will cut it into different pieces. You will polish it, and at the end, you will have this kind of pieces of selenide glasses or sulfide glasses. So it's pretty long to get a glass. It's like doing it for 2-3 days. But we developed several years ago a new way to make infrared glasses, but not only infrared glasses. Different kind of glasses can be by using this technique. So instead of using heating, instead of using temperature, high temperature, we have decided to use mechanical energy. So it's pretty interesting because using this energy and this technique, what we wanted to do is to avoid the use of single-use silica tubes, because I told you we have to break it each time. So what we have done is just to put all the starting elements, germanium, arsenic, selenium, etc., in a jar with milling balls, and we let it turn for several hours, around tens of hours. And at the end, you can get also a reaction during the mechanical stress. You have a reaction between all the raw elements, and you have at the end an amorphous powder, which is exactly the same composition as the glass. So instead of heating just by grinding the elements for several hours, you can get the same composition, the same glass. It's only powder, so then you have to make a bulk glass. And we decided to use something which is pretty new, which is a spark plasma sintering. So you will heat the powder and press it in the same time, and use also pulse current to make it faster. So you will sinter the powder, and at the end you will get a glass. And if you want, if you let a longer time, you can also make glass ceramic. So I will talk about glass ceramic later. And here is a picture of what we've obtained. So different glasses of different diameters. And using a thermal camera, you can see that it's perfectly transparent in the infrared. So this process was called Optima process. As I told you, actual process needs melting and quenching of elements, and then you have, to core the bulk, to cut it, to polish it. And so it's a long process. You lose a lot of matter, and using our Optima process, just by grinding, you can obtain the whole things, your amorphous powder, and by sintering, you will directly get the lenses. So fewer steps, better use of materials, and what is very interesting is here you can recycle all of the materials. So I've been contacted by a lot of companies who wanted to use this process. Because it's very efficient. The sintering steps last only for 2 minutes at 390 degrees C instead of 900 degrees C for 12 hours. And also what is interesting here, for this kind of composition, we have diameter of 8, 20, and 36 millimeter. While when you use it in silica tubes, the maximum that we can achieve is 9 millimeter, because after that we will get a crystal inside instead of a glass. So there is a strong decrease of the production cost, but also now we are able to do this kind of way using continuous production, and it's quick and easy shaping. Here is a presentation of the thermal imaging. And so this technology has been transferred in a company that the lab has developed 10 years ago, which is Diaphyr. And so what are the applications of these lenses? We can see here. Some of them, the small lenses, can be put directly on smartphones, so you will be able to have infrared lenses on your smartphone. So this is apps that you can already buy. It's pretty expensive. It's still 200 euros, 300 euros, but it exists. But the main application, of course, are military application. And since 4 or 5 years ago, we've developed a process for medical application, because in the infrared wavelength, all the organic molecules have their own signature by absorbing the light in the infrared. So here, what we can see in this picture is just a chalcogenide fiber. If you just put a drop of blood on it, you can detect some different kind of disease. So this is a thing that is commercialized now, and that is available in different hospitals. But for chalcogenide glasses, all the applications are not based on lenses. As I told you, it's easy to shape, so other specifications of these glasses are based on fibers. So I can show you how we can make fibers. So here is a small scheme of what we can do. It's a drop and then turning and then getting on a winding drum. But here I won't work. I had a small movie to present you, but I don't know how to share this. Sorry. So, well, on this movie, I don't know if somebody can tell me how to share this kind of video or not. But well,
Or maybe you do you have it separately?
yeah, I think so. Well, yeah, I can try with something. Oh, well, here
Oh, it's working.
it's working. Okay. So what you can see here is, so this is a preformed glass, and here at the furnace, so we heat the glass up to its glass transition temperature. It's making a drop, so it's in few seconds it becomes solid. So if it's solid, it's very thin here, so you can break the drop and get the fiber. Then you go through this kind of machine, which is just serves at controlling the diameter. You stick it on a drum, and then depending of the speed of the drum, you will be able to control the tension. And if you control the tension, then you will be able to control the diameter of the fiber. And this is the main parameter for a fiber, it's to control its diameter. And you can see at the end of this movie, at the end, we will get some hundreds of meters of fibers just using a preform of about 10 millimeter diameter and 5 centimeter height. So it's very easy to make fibers, and with very few meters, you can get a lot of distance of fibers. This is not the only way to shape the glass. Something we developed, I would say 3-4 years ago. It's a 3D glass printing. So it's very interesting to print glasses. It's not so easy. It has been developed by the MIT on window glass, but on chalcogenide glass, it's much more difficult because I told you that we don't want to see oxygen in the glass. So we developed some experiment under glove box or under natural atmosphere to get chalcogenide glasses. Why it's interesting? Because you can realize some very complex shapes. You can keep the infrared transmission. You will be able to produce pretty big quantities. You will reduce manufacturing cost. You will save production time. And what is very interesting here is that you will be able to use again the materials. So you can see on the top right some figures we've made by 3D printing. And what is funny here is we also made Dark Vador with a very thin design. And Dark Vador here is still transparent in the infrared. Here is another picture. It's a preform of fiber. So we are also able not only to make bulk glasses, but also to make some preform with specific design to make efficient infrared fibers. And here also is a small movie to show you how to make 3D printing of chalcogenide glass. So on the top, you have a furnace, which is just above the glass transition temperature. So it's around 300 degrees C. And then you print it. You can see the design will depend on what you want to get at the end. You will use a specific code to print it. And what you can see, it's still liquid, and in few seconds it's become solid because of the glass transition temperature. And at the end, you will be able to make the shape you want. So this is a very new process. We are able to make very specific design for lenses, for fibers, but not only. Okay, so I've presented some specific features about chalcogenide glasses. I will go further now to show you what we can do specifically with this kind of glasses. We still have some current challenges to face, and one of which is very interesting according to me, was the Helios project, which was a European project, a huge European project with many companies. What they asked us is to develop some infrared optics with high refractive index, higher than 3, to get autonomous car conception. So you hear the different levels of car conception, from the human to the machine, which can drive by itself. And what we wanted to get, it's a car where you should be able almost to sleep when you drive. Some propositions are already made using LiDAR here, but in fact, in the US, they got a lot of accidents and dead people because LiDAR doesn't work very well during the night and foggy condition, and that's why they wanted infrared lenses to control the car during the night. So I already talked about what can see human eye in the visible. And near infrared, we see a bit more, and we can see some traffic signs here. And some more, we can even see the car and also the people which are close to the car. So also we can add this kind of glass in the car at this place, and it will control the temperature, your temperature. And as you can know, when it's too hot in the car, you will fall asleep. So the car will manage directly by itself the temperature in the car. And also it will be able to detect when you will want to sleep, your drowsiness. And so by detecting your eyes, it will also make an alarm and tell you when you will have to stop. But using thermal imaging, you will be also able to have an instant recognition of body. You will be able to say if it's a dog, a human people, or what else. And also you will be able during the night to check the traffic signs, and the car will be able to adjust its speed according to the traffic signs. So at the end of the project, we developed some new infrared optics for automotive application. We developed some glasses with new elements like tellurium, sorry, and we used the mechanical milling and SPS, as I showed you before. So at the end, we obtain glasses with very high refractive index. They are mechanically resistant, low cost, and as you can see here, we shaped some lenses, and here is the device we obtain on automotive that are placed now on some pretty expensive cars, but it works. And so the car are close to drive by themselves during the night. There are other ways to change the optical properties of glasses, and this is another challenge to tackle. And I will start by the top right image here, which is Gorilla Glass. I guess most of you know what is a Gorilla Glass. It's what you have on your smartphone. Most of the smartphones have this kind of glasses. It's very resistant, it's very thin, and it presents very hard mechanical properties. How is it made? It's a simple glass, but they have improved their mechanical resistance by chemical treatment using ion exchange. It's pretty easy to understand how it works. So what they've done is to place a glass like this one, which is based on silicate, oxide, and sodium. And they put it in a melting bath based of potassium nitride. And after several hours or days, potassium, which is bigger than sodium, will enter the glass, and sodium will goes out. So when you put something which is bigger in a glass, you will have a compression layer on the top and some tension inside. And when you are doing this, you have strengthen the glass and get some better mechanical properties. But what is interesting for optical properties here, it's when you change the glass composition, of course, you will change the refractive index. And so we used this chemical treatment for optical purpose, and it's not very often that it's done. So what we have to know before is that in the visible and infrared, the classical lenses are based on homogeneous refractive index, and the power of the light is given by curved surfaces, as you can show here. And usually what you need for telescope and different kind of application is to have multiple lenses to obtain high quality image. So the main drawback here is the size of the optical system, which can be very big, and you don't have compact equipment. And when you need some very efficient devices in the infrared, you will multiply the number of lenses, like in the system where you need more 7 or more lenses. So it's not cost efficient, and it's very heavy. So we wanted to use green lenses, which means gradient index lenses. So which means that the refractive index will change spatially, and the light will be focused by changing the refractive index of the lenses. So here is a classical lenses, where the light change is deviate because of the curvature. But in our glass with a flat green lens, here it's very flat. When you change the refractive index from the center to the side, you will be able also to get the deviation of the light. So it's very interesting for us because you will give more freedom for the optical design and get very simple shaped. You will be able to correct thermal and chromatic aberration, which means that you will have better quality of images. You will also reduce the number of lenses in the optical device. Like you show here, you can get the same quality of image by using only 4 lenses instead of 7. So of course, you will lower the size, you will lower the weight, and you will lower the cost of the camera. How we can manage that in chalcogenide glasses is not so simple, because I told you that we want to avoid oxide within the glass. Well, what we have shown is that even by using some nitrate bath, it's only the potassium which will enter the glass and not the oxygen. So we will have different glass composition, and the potassium can enter in the glass. So at the end, we will have high refractive index on the side, and in the middle, we will have low refractive index. So we will have a gradient of refractive index in our glass. And well, this method is pretty long because it takes more than 2 months to get this kind of glass at very low temperature. And for now, it's not so efficient because we obtain a diffusion depth of only 2 millimeter, but the very first publication, they only got 25 microns. So it's a pretty interesting results. But at the end, we have a saturation of potassium after 40 days and crystallization. So we can't go upper than 2 months, because then it will degrade our glass. So we made a glass of 4 millimeter diameter here. We used an infrared camera, an infrared source, and a grid here. So this is the base glass, and we can see that we are deviating the light when we are using the green lenses here. And at the end, so just by using a flat glass and ion exchange, we are able to get new lenses, very flat and with a good curvature of the light. So we obtain a glass which is cost effective. We don't need to lose a lot of material during the process by grinding it, and we can recycle it. So it's very interesting. And so this process is very efficient for military application, because you can understand that you don't want to have 20 lenses on this kind of devices for soldiers. And the main one is, of course, still for military application. If you can lower the cost, but even more lower the weight of lenses and of the device on the drones here, well, it's for sure much more interesting. So this kind of concept is now developing by Umicore company for this kind of application. What about infrared fibers? I will show you some example of infrared activity in the lab using infrared sources by mid-infrared supercontinuum, a colleague, Joan Trolles. They've developed some very interesting fibers. As you can see on these pictures, they've started in 2006 with some specific features of fibers, different kind of design, and they develop new design each time for, at the end, getting 12 years after something that they sell, which is a QC laser mid-infrared. As you can see, just by using light in the infrared, they are able to make a supercontinuum source in the mid-infrared range, which means by using light from 6 to 8 microns, they've developed a source which light from 2 to about 10 microns. And so how they develop that? It's just by using the infrared transparency of the fibers, of course, but also because when you use some heavy elements like chalcogenide ones, you will have some specific optical properties. And in this case, by using selenium, you will have strong nonlinearities inside the bulk, and you will be able to develop different modes of propagation of light. And this is with this kind of propagation, with this kind of modes, that you will be able to develop new infrared sources. And so this is very interesting for fibroscopy and different medical application. Other application for fibers in the infrared. Here is CO2 detection by using rare earth doped fibers. It's developed by Virginie Nazabal. So they recently produced an all-optical gas sensor in the near infrared for remote detection over long distances, over several hundred of meters, even some kilometers, thanks to a new way of detection. So it's pretty easy to understand how it works. They have developed fibers with different rare earths, and this rare earth will emit at a specific wavelength where CO2 will absorb. So we will clearly see when there is a decrease of light in the fibers due to CO2 presence, and they will be able to quantify even with a long distance. So this is what is done here. They want to detect some caves of CO2 for pollution, etc. And so they can do it using this kind of device, using fibers, infrared fibers. So this is also a European project that is under development, and they are transferring this technology to a company. What else concerning chalcogenide glasses? I want to go further up to glass ceramics and ceramics. All of them are multifaceted materials. I will just show you what I've done when I've started my career. I've mainly worked on chalcogenide glass ceramics. So glass ceramics is just based on glasses and nanocrystalline particles within the glassy matrix. So I have started in 2003 in my PhD. I've developed some glass ceramics that you can see here to enhance their mechanical properties. Then I've developed some other application to make some lasers in the infrared. Some others, glass ceramics for photovoltaic photocatalysis application, but it's not only for that. We also have some project to make some electronic devices like DVD, etc., for to make some reconfiguration between the glass and the crystals. As I told you, we obtained some green lenses, and now we are working on new topics based on, I would say, eco-friendly applications. So I've shifted my thematic from optical properties to, I would say, electronic, because I'm working on solid-state electrolytes, which are also based on chalcogenide elements like sulfur. So we'll mainly develop this part now. Why we want to use chalcogenide materials in batteries? As you all know, there is an increased consumption of energy, and it will be worse and worse in the next years. Furthermore, you all know that well, there is a global warming, and if we don't do anything, then it will be worse and worse. So we have to develop some renewable energies based on the sun, but not also. But the main problem now is to store the energy, and the batteries which are developed are not so efficient or can be dangerous. So we have decided to work on new kind of batteries. Here is a brief history of batteries. As you all know, the first one with lead acid, and to start our cars today, we still use this kind of battery, which shows that it's not there is not huge advances in the domain of batteries. And then we use nickel cadmium or nickel metal hydrure batteries. And the very last generation is what we are all using for the everyday life. It's lithium ion batteries. But as you have seen some picture, probably they can get some lithium dendrites. And sometimes you will have safety issues like fire, like explosion, etc. So we have decided to develop all solid-state battery based on lithium and sulfur to avoid the leakage of liquid batteries, to avoid its toxicity because of leakage and pollution. And also the main problem of liquid batteries, it's formation of dendrites, as you can see here on this part. And when there is a short circuit, then it will be flammable and there is a risk of explosion. By using all solid-state batteries, we will have more efficient and more safer materials. Also, using lithium-ion technology, everybody says that the limits are close to be reached. So we want to develop a very new generation of batteries, like this kind of all solid-state batteries. And the way to use them is very similar to the one of the liquid ion batteries. So here is an example of what we will be able to do with solid-state batteries. We'll put back the laser pointer. So what we want to use, what will be the next step, it's to use an anode of lithium and to put some glasses or glass ceramics based on sulfur, so based on chalcogenide elements containing lithium and phosphor in the middle of the batteries, and having an interface with other chalcogenide elements like the TiS2 here. So here's the picture to show you where we are with lithium-ion batteries. We are using graphite, and we are using some kind of cathode based on lithium, cobalt, and oxygen. So it's where we are. And if we look at the specific capacity of cathode and anode, it's where we want to go using sulfur and lithium, which means that we want to increase by 10 times the capacity of batteries. So we should be able to get car having an autonomy of several thousand of kilometers and having the same cycle lifetime, which means that we could get some cars having batteries for more than our lifetime, more than 100 years. So also solid-state batteries appear as a good alternative to liquid electrolyte. sulfur-based glasses and glass ceramics present very high performances because they are here using lithium, but we still have some challenges to tackle, like the interfaces between the metal anode and the solid electrolyte. So for now, the current solid-state batteries, we obtain some pretty good ionic conductivity, but not as good as ionic liquid. We use a very thick electrolyte, which is not good. We have low battery energy density, and sometimes it's cracking after cycling. However, we have a good electrochemical stability. We have an energy density which is pretty good also. We have strongly increased the safety because we don't have explosion or fire. It's waterproof also, and we can work in a very extended range of temperature. So I would say in the main goals to reach, some are already reached. I mean, the safety and temperature ranges. The one in blue are still interesting, but not perfect. So we have a good energy density and power density. We will be able to have a better lifetime for the batteries, but for now, and this is the main problem for batteries, whatever lithium Li-ion batteries or also solid-state batteries, it's very expensive. And the main problem is this one is that we are not able to recycle them. So the research we are doing is to improve the cathode materials. We also want to improve the surface coating of cathodes to avoid the parasite reaction. So we will use some chalcogenide elements here. What we want to do also is to change the composition of the electrolyte, so to develop some new sulfur-based glass ceramics. And also, what is the biggest challenge, I would say, it's to stabilize the interface, and there is a lot of research. And without reaching this goal, we won't be able to produce all solid-state batteries for cars or other devices. So what more with chalcogenides in our lab? We have developed since pretty recently some solar cells. So the aim is to convert light into electricity. So we are using not sulfur, but selenium, Sb2Se3. So we were the first team working on homojunction of Sb2Se3, and we developed some solar cells with yield which are not perfect, but still higher than 10%, which are very cheap and very simple to make. So there are a lot of papers on this kind of solar cells. And we are also working on thermoelectric materials based on heaviest elements like telluriums. So we are making some new glasses. We are also doing some glass ceramics by introducing some nanoparticles within the glassy matrix. And also we are developing some thin film. I didn't talk about thin films of chalcogenide glasses, but there are a lot of work to do also on this point. So to conclude my presentation, as you see, we still need for permanent innovation in the field of materials. It's not the ideas which are lacking, but we still have problem of material supply. For example, lithium, it's a huge problem, but also cobalt and etc. We also have some regulation to follow. So we have a lot of restriction for usable elements like arsenic, antimony, etc. So we need to find clean and sustainable alternatives. What is interesting is that we have more and more national and international calls related to environmental impact, and that's the main point. And so for prospects, I would say that future is in the end of the future researcher. So design it as you want using fair science. So I would like to thank all the fundings we got in the last years and the PhD who worked on the result I've presented. And also, I would like to thank you for your attention. Maybe I was a bit long.
But it's perfect. Well, thank you very much for your brilliant talk. It's not fundamental research, we see. It's
No,
really, really applications, and you
yeah,
covered most of the application possible in the area, I think. Really good. Thank you very much.
you're welcome.
So if you have any question, do we have any question in the audience?
Hello, sir.
Hello.
Yes, Wemi.
Yeah. Hi, sir. I have one doubt.
Ask your question.
Uh, Actually, we have some organic materials having glass behavior. So, can we dope them into this people and will they be stable? Like if we get an hybrid glass, organic and chalcogenide hybrid glass, will those systems will be stable enough?
Well, this is a very interesting question because we were talking about that with Surier just before the presentation, and it's not very easy to do because there is a big shift of temperature range of usage between organic compounds and glasses, and so when we want to place organic particles or in chalcogenide glasses, what can happen is to destroy them because the melting process needs high temperature, and so it's not easy to place them within the glassy matrix. But I showed you what we can do is to sinter some glass powder at pretty low temperature. So when we sinter glass and organic compounds, we can get some composite materials, keeping the properties of organic compounds and also the infrared transmission. So there are some research on this topic.
And moreover, the chalcogenides are more constituents in these quantum dots kind of materials, and they are also luminescent. So, can you dope them also into this matrix? Will they give any inherent properties here?
Well, yeah, this is one of the most interesting compounds to dope them. You can use a lot of rare earths of cations to dope them, use quantum dots or whatever you want, add silver nanoparticles, and you will get a lot of different kind of application in the infrared. You will be able to improve the luminescence efficiency doing lasers. You will be able to do supercontinuum by doping them. So yeah, there are many things to do by doping this kind of materials.
Thank you, sir.
Yeah, thank you, Swami. Any other question?
Actually, I don't have
Yes.
a question in particular, but I just want to thank Dr. Lauren for the nice presentation. And I'm Ali Arçın Ersun'da. I'm the co-director of the Yıldız Technical University Glass Research Group. So we are also working in the field of glass, but mainly, yes, okay, mainly with the oxides, okay, like silicates, phosphates, borates, and some heavy metal oxides. So I have a question in mind. What about doping some quantum dots into chalcogenide glasses? I mean, have you ever tried them to, boost some of the optical properties? I mean, forming some, nano-sized crystallites within this amorphous matrix could be quite interesting. Have you ever given a try?
Yeah, we did it. We got some quantum dots. Usually it's what we used is to use it on fibers or some this kind of elements to improve the signals in the infrared. It's not easy to get some nanoparticles within the glassy matrix because
Yeah.
usually, this is the main problem. Contrarily to some other glasses, the crystals can develop pretty fast, and so it's difficult to maintain a small size like nanoparticles and quantum dots. But yeah, there are a lot of work on doping some chalcogenide glasses with zinc selenide or PBSC, etc., to get some quantum dots and have this very interesting optical effects.
Yeah, could be very interesting. Yeah, thank you very much. It's a very inspiring talk, and we would be glad to host you here at Yıldız Technical University if you have any chance to visit us.
Thank you very much.
Thank you.
Hello, sir.
Thank you very much. Any other question?
Hello, sir.
Yes, Mami?
Is this glasses are etchable? Etching will get etched.
Yeah. Yes, of course. It's not easy because you will have to use. It's very resistant. It's much more resistant than oxide glasses. So you will have to use HF. Even if HF, it's difficult. So sometimes with NaOH, you can also destroy a bit of the glass, but these one are not so easy to destroy.
Okay, thank you.
Yeah, this was my question also. Do you have any idea of the lifetime of your materials?
Well, it's a glass, so it's very, very long. I mean, the glasses, the first one I presented for cars, they've been developed 45 years ago, and we still have some glasses made, I guess it's 50 years ago in the lab, and they are still very nice.
Okay, so it's a really lifetime.
Yeah,
actually.
it's a long lifetime. So I guess if we come back in 1,000 years, they won't move.
Okay, thank you very much. Okay, and I was curious to know if you said that metals like lithium and rare metals are quite difficult to find now. But what about minerals, selenium or telluride, chalcogenide? Do we have? Are we run out or?
No,
It's
for
easy to
sulfur,
find?
selenium, tellurium, it's still pretty easy to get them because they are extracted in almost all over the world, contrary to lithium and cobalt. And so there's no tension on this kind of minerals. Not for now, I would say.
Okay.
It's much more complicated for the minerals which are used for batteries application now.
Okay, thank you. Any other question? Okay, so if not, I think we can stop here the presentation, your conference, Laurent. Thank you very much for accepting to talk to these grad talks. It's thanks to Professor Belkis Bilgineran, who is director of the Institute of Chemical Science, and also Nihan Kahraman, she is vice director also of the Institute. So they organize these grad talks. So thank you very much for participating.
Thank you. It was a great pleasure.
Thank you very much. And merci beaucoup.
You're welcome.
Yeah, it was you also.
Thank you very much.
Bye bye.
Bye.
Bye.